Welcome back, everyone. I hope you all had a good weekend. So we're gonna today get into the very last chapter of the book. So we've made it through all 12 chapters, which is pretty cool. And we're gonna be talking about runtime monitoring. We have talked about a whole bunch of methods up to this point for validation. And all of these methods we can kind of call offline validation methods. So these are things that we would do potentially before deploying the system into the real world. So we might find failures, estimate its probability of failure, try to get some formal guarantees, do some explainability. And we're doing all of this based on some model of the world that we made, which we talked about some ways to make models in like the second and third lecture. But we kind of said it's really hard to model all possible things that we might see, and inevitably this model is probably going to miss stuff, especially if we're trying to model systems that operate in very complicated environments. So for example, cars that operate in these various road environments. So for example, the video on the left here is like this crazy edge case that like this Waymo vehicle sees, where it's like, I don't know, I'm sure that like giant random fountain in the middle of the road was probably not something that was in the model. Maybe like a fire hydrant exploded or something. And then it kind of just drives up to it, stops, and doesn't really know what to do. But at least it doesn't go through it. And then I think this video on the right here is one that Anthony showed during his guest lecture. But basically what's going on is there's like a Tesla that's driving down the road and it keeps detecting all these traffic lights, and it turns out that it's following a truck that was transporting traffic lights. So again, these are just like these crazy edge cases that like we can try as much as we want to incorporate every possible edge case into our model, but at some point we're just like not going to be able to think of every possible thing that could happen. And this kind of brings me back to a slide from my second lecture, where we were talking about modeling, and I was talking about like my general thoughts on making models, and I was identifying some of these key challenges here. And I said kind of one of the main key challenges is that we need to end up with a model that's expressive enough to capture all possible scenarios that the system may encounter. So random water shooting out of road or traffic lights on a truck. We would want our model to be able to capture all of these possible things. And I mentioned to you that basically every single time I give a talk on validation, it seems like I always get at least one question where someone comes up and they say, totally valid question, which is just, how can I capture all possible scenarios that my like crazy whatever system is going to end up in? Like, I don't even know what they all are. Like, I probably wasn't going to think of that traffic lights on truck thing. So how do I deal with this? So again, it's a totally valid question because it's a really hard thing to do. And so my response, I told you in the second lecture, is always like, yeah, it's totally a problem. This is really hard. But I mentioned that there's some hope here and that you should stay tuned for the runtime monitoring chapter. So here we are. So runtime monitoring is going to be the solution here. So again, we kind of do our best to model the world when we do our offline validation, but we're inevitably going to miss stuff. And so my answer to all of this basically is runtime monitoring. So you may have seen this wonderful quote from Hitchhiker's Guide to the Galaxy by Douglas Adams, that's the ultimate answer to life, the universe, and everything is 42. I would like to revise it slightly and just say that the ultimate answer to life, the universe, and everything is runtime monitoring. So I'm a big proponent of runtime monitoring. I think it's going to be absolutely necessary to kind of catch all those things we didn't catch in offline validation and actually deploy our systems safely in the real world. Okay, so with that, like the goal of runtime monitoring is to basically flag situations that might be hazardous when they occur so we can trigger some kind of fallback mechanism. So we should ideally understand that we're in a situation that maybe we didn't validate for, we haven't seen before, we don't know what's going on, and we can trigger some kind of fallback mechanism. So that could be something like entering into a safe mode. Maybe if you're driving, it's just like stop the car. Maybe if you have like some human operator that's in the loop, you could transfer control back to this human operator. Lots of different things you can do. We're not going to talk super specifically about that. But what we're going to focus on today is like, how can we flag these situations that might be hazardous? Okay, so that kind of brings me here into the plan for today. So we're going to talk about lots of different ways that we could do this. One way is operational design domain monitoring. That's what we'll start with. Then we'll get into uncertainty quantification. And there's two different types of uncertainty we're going to talk about. The first one is output uncertainty, and the second one is model uncertainty. And then super briefly, we're going to talk about failure monitoring. And then this is my last lecture, so we'll wrap up the course, so sad. Okay. So let's jump in with operational design domain monitoring. Okay, so this idea behind, and by the way, I think some of you may have heard of like out of distribution detection techniques. There's different ways to kind of categorize this. I think this is very similar to what you would think of when you maybe hear out of distribution detection, so you can kind of equate these two in your brain. But for our purposes, we're going to call this operational design domain monitoring. And the idea is that systems have these things called operational design domains, or ODDs. And these are basically the set of conditions under which we've designed our system to operate safely. So this could be like daytime conditions with no rain or something like that. And basically the idea here is like, what this could be is like actually the set of conditions that the model that we used for validation covers. So we created some model, we validated against it, and that model contains some set of conditions, or models some set of conditions. And then the idea is like, if we then operate outside the ODD, or the operational design domain, then we are outside of the conditions that the model we used for validation covers, and so our validation results may no longer be valid. So basically the general idea here is just that we want to flag situations that could potentially be us operating outside our operational design domain, and in that case, we would have basically no more guarantees on safety, or like our validation results don't mean anything anymore. And so, for example, like there's a decent chance, I would imagine, that truck transporting traffic lights was not in the operational design domain that Tesla defined for their self-driving car, understandably, because this is like a weird, crazy thing to kind of contrive in your mind that you would have had to come up with. And so kind of the next best thing that we can do, I would say, is to monitor at runtime whether a system is operating within its operational design domain, which is a non-trivial thing to do, and we're going to talk about different methods to do this, but this is kind of our goal. Okay, so in order to monitor whether or not we're in the operational design domain, we have to figure out some way to like represent what this thing is. And there are multiple ways to do this. One option is to just use a bunch of hand-designed features. So for example, maybe for the aircraft taxi system, we could say something like, we designed it for days where there's no clouds in the sky, there's no glare coming from the sun, it's daytime, and it operates on taxiway A. So maybe this is like a super restrictive system, but maybe that's all we tested for. And if it turns out that we're outside of these conditions, then we can't use the system, or we say that we're outside the ODD. And so this is something we could just write down ourselves and maybe even check ourselves on the day of before we like go deploy our taxi system. And then there's also one more way that we could define the operational design domain, which is to take a data-driven approach. So instead of ourselves hand designing all of the different features that say what's in the ODD, we can take a bunch of data from, maybe it's all the data that we used for our validation. So maybe like for the continuum world, maybe we like simulated a whole bunch of trajectories, and we have all of these trajectories that we saw during our offline validation. Or for example, maybe for this like intruder detection, aircraft detection system, we have all of the images that we trained it on, all of the images that we validated over, and that defines the operational design domain of the system. So these are both like equally valid ways to do this, and in some cases, you might want to use one versus the other. Yeah.
Two questions for this. So first of all, this is respective of, or like ignorant of the model that we actually use, right? It's just something about the problem space in the data. Okay, and then for the second approach, where's the design when you do data-driven definition of your design domain? Because I feel like when you have hand-designed features, it makes some sense to say I design the kind of domain that I want to work on. But I feel like the right approach is much more the like distribution, out of distribution perspective on this question here.
Like the word design is like what's tripping out?
Design and the right.
Well, I mean, the data you use is a design decision, I would say.
Okay.
You can call it the operational data domain. If that would feel better.
Or the distribution of samples that we need to work at. Okay, anyways, yeah.
Sure, we could say it comes from a distribution. That is, we will actually make that assumption in a few slides.
I feel like this is the difference between out of distribution, which is kind of the right side, and out of the design domain, which is the left side.
I would say yes. I think out of distribution detection, in my opinion, is kind of a subset of this, but I think the way people use the term is like pretty loose, so it depends, yeah. But we are going to assume a distribution soon, yeah.
Actually, I think maybe extending or reframing Lillian's question, do we have to do anything with the data that we're doing in a data-driven approach in the sense of like, does the data also have to be some kind of integral part of model design, or can it just be some data we think?
I think ideally, like you want your data to represent where you expect your model to work.
Sure.
So,
do you want, like, is it only, like, do you only have the guarantees if you say, like, train your model to learn from this data, or sort of, is there any notion of, like, we have to use this data somehow in the design of the policy, or at least in that evaluation?
I think it depends on, like, what kind of confidence you want to have in your ODD monitor. Ideally, I think you would use the data that you used in validation, because if you use the data that you used for validation, then you know I did all this offline validation using this data. So I have all of these offline results that tell me how safe I should be given this data set. And now I want to know when I'm operating online, am I outside of a region that I validated over? So that's like what I would do. Okay, so there's one, so they're both equally valid kind of depending on maybe the situation that you're in and what's easier. But I will say that this one on the left here, the hand design features, it does require domain knowledge. So it requires us to sit down and write out like what are all the conditions that we have designed our system for. And it can be quite difficult, I would say, to like enumerate all of these. So we're going to focus for the rest of this lecture on this kind of more automatic way of doing things with these data-driven approaches. And so we're going to start with this continuum world example, and we're going to use it as kind of a running example. So basically what we've done is we've assumed that we've done some offline validation. So maybe we just did a very simple offline validation in this case where we just did a bunch of rollouts and saw that they all reached the goal and none of them reached the obstacle. And we're going to say that, okay, if we're in the operational design domain defined by all of these rollouts, then we expect our system to be safe. And if we're outside of it, well, we haven't validated over that, so we don't know what's going on, and we probably want to like flag that situation. So we're going to use this as our data. And specifically, we'll just take all of the states that we saw when we were doing all of these rollouts and use that as the data points to define our operational design domain. Okay, and so basically, our goal here is then to determine the set of states, so the set of any of the states in this outer square here, that are part of the operational design domain. And kind of logically, the idea is that states near states that we saw during our offline validation should probably be within the operational design domain. So with that, maybe kind of the first most obvious thing to try then is to just say that the operational design domain is the set of points whose nearest neighbor in the data set is within some threshold distance. So basically we look at any point in here, we look at its nearest neighbor in the data set. If it's above the threshold, we say it's outside the operational design domain. And if it's within the threshold, then it's within the ODD. And then you can see that like the blue shaded region here, given some threshold, would be like the operational design domain that we define. So then if we're operating and we find ourselves in a state out here, we can flag it and say that we're not in an area that we've explored before. Okay, so let me show you some different things we can do with nearest neighbors. Okay, so this is the same plot we had before. Zoom in a bit. Here is, so here we can vary this threshold distance that we use to decide whether or not to include a point in the operational design domain. So if I decrease this threshold, do you think that the operational design domain will become more or less conservative? And conservative meaning like it only includes points near the points we've seen, and less conservative would be like it includes a whole bunch of extra points. So if I decrease the threshold, more or less conservative?
Sorry, the threshold.
This threshold, which is the distance that's required, it needs to be this close in order to be considered in the operational design domain.
Okay, more
conservative. Yep, exactly. So we're going to get like less and less area that we cover. We need to be closer and closer to these points, and then to the point where like we could basically just say that the points we've seen are operational design domain. If we haven't seen this point before, it's not. And then, of course, if we go the other way, we get these kind of very big design domains that maybe include areas that we wouldn't want. So you got to kind of tune this threshold. Another thing that you can do with nearest neighbors, which is kind of cool, is you can, so here we're just showing like points where the closest neighbor is within some threshold, but we could up that requirement. So we could say we need 2 neighbors, we need 2 points to be within some threshold, which would allow us to kind of get rid of some of the outliers out here. So if I decrease this back and let's increase the number of nearest neighbors we require, you see it kind of gets rid of like some of these outliers that are just kind of by themselves because we're requiring 2 points to be nearby. And we can continue to increase this and you'll see it kind of gets rid of some of the ones on the edge. So it just depends on how you want to define it basically. Okay, so here it is implemented in code. We basically just compute the nearest neighbors and then check if they're within this threshold. Okay, but what do you guys think are maybe some potential drawbacks of this nearest neighbors approach? Yeah.
Maybe too conservative. In the sense of I'm only looking at the points I've seen and also only directly next to them. Or if you set your threshold to be high, then it also could be like it's basically not adaptive. It's just either given your threshold, it's either way too conservative or way too general.
Yeah, I mean you might be able to find a good threshold depending on the system you have. But yeah, you have to tune the threshold. I guess I'm thinking more in terms of computation. What might be a potential drawback of this approach? Yeah.
You need to compute nearest neighbor distance for all points.
Yeah, exactly. And there's actually one more if anyone wants to try to guess one more issue. Yeah.
In high dimensions, distances become very strange in high dimensions.
Yeah, I kind of knew you were going to say that. But that's not what I'm doing.
But also, I think KD tree calibrated.
Yeah.
I think the data structure KD tree gives you a very fast lookup even for very large numbers of points. I don't think it's a big computational problem.
True. Okay, so the true computational problem is it requires storing the entire data set in memory at runtime. So even if you have the KD tree, you need to store the entire data set.
I'm sure there's data structures.
No, surprisingly, this is actually our biggest bottleneck for Ragdoll. It's not any of the language model stuff. Nearest neighbor search is actually our biggest bottleneck for raw for Ragdoll. So it's actually quite extensive.
But the high dimensional thing, do keep that in your back pocket because I'm going to talk about it later. I just don't want to get to it just yet. But it totally is also an issue. Okay, but yeah, so basically the computation can be an issue if we have to like store the entire data set in memory. We might not want to like take that on board with us when we deploy it at runtime and have to check every single time, find like the nearest neighbor. Okay, and so
but the KD tree could reduce it to like logarithmic time, right, for each.
Yeah, so it helps. We still have to store the tree. Okay, and so one way though that we could potentially improve this without losing too much accuracy is to just cluster all of the data. So we could run like k-means clustering or something like that, cluster all of the data, get all of the cluster centers, and then just use those data points to define the nearest neighbors. So we'll say you need to be within some distance of the cluster centers, and then you don't need to, you only need to store the cluster centers, and you only need to check distance to all the cluster centers. Okay. So that's one option. Another thing we could do without trying to upload the whole data set or cluster centers onto our robot or whatever we're deploying is we could use a more compact set representation such as a polytope. So does anyone, given all of these points, does anyone have an idea of how we might define a polytope from them? Yeah. Yeah, exactly. You could just take the outside vertices, or in other words, the convex hull of the data. Okay, but there is one kind of issue with this, is like our ODD seems like it's kind of non-convex, and if we just take the convex hull, we're including this whole region there that doesn't really seem to be part of the operational design domain. And so one thing that we could do instead is like cluster the data. So maybe we cluster it into like 2 different clusters, the blue one and the purple one. And then we take the union of the convex hull of both of these clusters, and we get like a nicer shape. And we could just do that with like more and more clusters to get a better shape. Okay, so I'm going to show you in a second what the algorithm looks like for this. But before I do, I want to show you a quick Slack conversation about it. So when we were writing this chapter of the book, I messaged and I said, okay, so hear me out. If we do decide to include algorithms for some of the ODD monitors, we were still debating, we could have an algorithm like this, looks like this. It's a hull monitor. And then replied and said, you know, I'm absolutely on board with this. I love it. If the hull monitor's checks pass, it could send a hull pass flag. And this is how I know I work with the absolute best people in the whole world. So, yeah. So here it is. This is like the one joke from this class that actually made it into the book. So here's our hull monitor. If you're having trouble picturing this, there you go. Points inside, outside. And it really doesn't like the eye and monitor, which is kind of strange. But yeah. Okay. So did anyone have questions on the hull monitors? Okay. So one more option for defining the operational design domain is to use the super level set of a function. So now we're going to talk about distributions. So what we could do is define it as the super level set of a distribution. Super level set, if you're not familiar with the term, it's just all the points that result in a function value greater than some value. So just think of like, if you had like a plot of a function, just like chop off at some value, and it's all those points that correspond to that value or higher. And so what we could do is just like fit a distribution to our data. So maybe we fit a multivariate Gaussian to our data set. And then we say, we'll take the super level set of the probability density of this distribution. So we'll say if the density is high enough in this distribution at our point, then we'll include it in the ODD, otherwise not. So taking the super level set would give us like some set like this. But this doesn't look great. And the kind of caveat here is that you need to make sure that you select a model class when you're selecting this distribution that's expressive enough. So a multivariate Gaussian doesn't really fit this data set very well, but a mixture of multivariate Gaussians fits the data pretty well. And so we could take the super level set of this mixture, and then we get a pretty nice definition of our operational design domain. And one thing that's kind of nice about this is it can actually easily kind of trade off between these high density and low density regions. So if we're like, we don't really want to include the regions of low density in our operational design domain because we validated over those, but like not super significantly because we never really saw these states very much, we can easily trade off by just changing that threshold for the distribution. Any questions on that? Yeah.
You're making the super level set, but the super level set itself doesn't have like the great threshold.
Correct. So yeah, you basically throw the distribution away when you create this, because typically right now all we're trying to do is have like a binary flag, like is it in the ODD, is it not? You could imagine, like depending on how you deploy your runtime monitor, you could keep around the distribution and try to use that value to do decision making as well. It just depends on your task. Any other questions on this? Okay. Okay, there's one other way you can use this super level set idea, and that is to take the super level set of a model that's trained to output a likelihood of a point being in the operational design domain. So for example, we could gather a whole bunch of data, we could keep the data we had in the operational design domain, then we could gather a whole bunch of data outside the operational design domain, and then train a classifier to take in a point and say, is it outside or inside, and output a probability of that. So maybe we get a classifier with probabilities that look like this, and then we can just threshold that probability and say if that probability is greater than some value, we'll say that it's inside of the operational design domain, and we get something like this. What might be a drawback of this approach? Yeah.
You
have to go for the distribution each time, and if your system is way too complicated, then you either have to make a lot of partitions or a lot of very fancy distributions.
You might need a fancy distribution, but specifically for fitting this classifier, what did we need? What were all those like red data points?
Like stuff that doesn't need to fit.
Stuff that was outside of the operational design domain. So basically we had all those white data points. All the methods up to this point, we just used the white data points, like we fit a distribution of the white data points, et cetera, et cetera. But here, we had to get all of these red data points from outside the ODD, then fit this classifier. And the problem is, like, if we had all of that data from outside the operational design domain, we probably just would have designed our system with that data. So, yeah.
Wait, no, but like you go and falsify your system, and you have a bunch of stuff that's like going to fail, and then suddenly you have both in and out of the ODD.
I would say the ODD is everything you saw during validation, whether it failed or not.
Oh, I see. Okay.
Yeah, and so there could be states like we just never even saw, like a truck transporting traffic lights is kind of the idea here. And so we want to say, so the blue is like everything we've seen, whether it failed or not. In this case, none of them failed because they all made it to the goal. And we just want to say, like, when are we in a situation that we haven't seen? But then to train this, we would need data that we haven't seen, which is like kind of the problem. Yeah, exactly. That's kind of the issue with this approach. So sometimes like you can get a little bit of out of distribution data. Like for example, say you had a taxi system that was trained to operate during the day, but you have a few images at night. So maybe you could try to train a classifier to like distinguish the ones that were at night. But if you had a whole bunch of images of the taxi system operating at night, you might as well have just trained on those images. And so a lot of times it's not super useful if your method for operational design domain detection requires data from outside the operational design domain, because you typically don't have it. So it's just something to keep in mind. Any other questions on this? Yeah.
I think the biggest issue with this is that it's not always a given that you have a compact and useful state representation in vector form. So in any vector space, like take images for example, you're gonna flatten it and do it in pixel space.
Yeah.
That'd be ridiculous. Do not do that.
Right. Let's
So
go
you have
right to the next slide here. So this all works really well in low dimensions, but things get a little weird in high dimensions. Specifically, ODDs defined by images. So good point. So yeah, that's exactly where we're headed. So we'll satisfy you a little bit as well. I totally agree. It's like way harder, and it's way harder mostly due to this cursive dimensionality where the volume of the space that the data must cover increases exponentially with the dimension of the data. So for our taxi images, for example, they're like 4096 pixels. So we have a 4096 dimensional space that we now need to cover with all of our images. And that's just not very easy to do. So we're gonna need a whole bunch of data if we wanna adequately cover that space. And then secondly, as you were kind of pointing out, and as you were kind of pointing out, is that like distance metrics tend to lose meaning once you're in a space like this. So for example, what is the distance between two images? Is it like the Euclidean distance between vectors of pixel values? This isn't super obvious, and like a lot of times you want more of a semantic distance measure between two images, but this is just like in general not an obvious thing to do. So you need to be careful when you scale up to high dimensions. So there's a few things you can do about this. One option is to just kind of like brute force it and just get more data and get better models. So you could just try to use something like, maybe a Gaussian's not gonna work, but you could try to fit like a normalizing flow. Although there's been shown that there's issues trying to do that as well. If you're interested, you can talk to me later. But this is one option. You could just try to have better models that scale to these high dimensional settings. Another option is to assume that your high dimensional data, like your whole set of images, came from some lower dimensional manifold, and then try to find that manifold and do all of your, define your operational design domain in that like lower dimensional manifold. So what does that look like? Here, let's say we took our 4096 dimensional taxi images and we used some dimensionality reduction technique. So in this case, we used an autoencoder, but there's lots of different techniques you can use. I'm not really gonna talk about that. But here we basically took this 4096 dimensional image and we projected it down into a 2-dimensional space. So this is completely visualizing the new dimension of the images. So we have 2 features here. And so this image, for example, would map to one of the points in this 2-dimensional space. And then a bunch of other images that look like it, but from different angles and cross-track on the runway, will produce different points in this lower dimensional space. And now this is 2-dimensional. Distance seems to make a little bit more sense here, and so we could just define our operational design domain in this lower dimensional space. So maybe using like nearest neighbors or any of the other approaches that I just talked about. And then the idea is, now when we get a new image at runtime, so for example, this image here, this image actually doesn't really look like this image here. It's pretty like saturated. Maybe there's like some weird sun glare that's causing this, but it's super bright. We can barely see the edges. This is not part of our operational design domain. And it turns out if we project it into this lower dimensional manifold, along with a bunch of other images that look very similar, we get the red points that you see here. And so now we can actually see that the image, when we project it, is not part of the operational design domain. And so we would, at runtime, be able to flag that and say, hey, we got a point that's not in this lower dimensional manifold, and so we're going to flag that as outside the operational design domain. But there is one issue with this. So let's say that we got this image instead. This is also not in the operational design domain, because this one's actually super dark. It's more like we were doing this at night or something like that. It's not in our operational design domain of daytime images, but it turns out if we project this into our lower dimensional manifold and a bunch of points like it, we get all of these yellow points here, which actually kind of projected into a region in this manifold that's part of the operational design domain. But this is not the behavior that we wanted. And for example, like this white point here is like another image that's actually in the operational design domain. And they project to points very close to each other in this lower dimensional space. It turns out there's a name for this. It's called feature collapse. And the idea is just when you project down to these lower dimensional spaces, there's no guarantee that these like distinct sets of images are like actually going to remain separated in these spaces. And so you need to be careful, because it worked for these like saturated images, but then all of these dark images actually collapsed to a region inside of the operational design domain, defined by like our daytime images. So it's just something to be careful of. Any questions on that? Yeah.
Yeah, I was wondering, I think some people also use, like you get some embedding of your, which I guess again is like a low dimensional representation of your images, and then you do like cosine similarity. Like how would that fit into this?
Pretty similar. So I think like that would just be, so this I would consider to be a 2-dimensional embedding, basically. And then we're using Euclidean distance, but you could use cosine distance instead to define like the nearest neighbors.
Yeah.
So it would be a similar
But
thing.
you wouldn't have this feature collapse, I suppose.
I think it would. Like the cosine distance between these yellow points and this white point is still going to be quite small. So I think you still have an issue of feature collapse in that case. Yeah.
Are there ways to detect feature collapse other than just looking at the data?
I would say there aren't really good ways to detect it other than like when you're testing, you might notice it. But that's kind of why it's a problem, is because of the fact that you can't detect it.
And also, this is still irrespective of the model that we want to validate, right? So this is just a function again of the data,
Yep.
and whether or not our model will actually work now on the entire manifold or something like this, we haven't made any statement about that, right?
Yeah, exactly. So that's what I'm saying, like the data you use to define your operational design domain is ideally the data that you saw during validation, during your offline validation. So you've run probably a failure analysis on that data. You've run formal methods on that data or something. And now, this is how I expect my system to perform in this region. And if I'm outside that region, there's just no guarantee, basically. Okay. Was there any other questions on that? Yeah.
Are they just kind of arbitrary?
They're just like arbitrary. So it just trained like an autoencoder, which like goes from high dimension, low dimension, and then tries to project it back to high dimension, and it's just whatever comes out in the middle there. A lot of times it's not super interpretable. Yeah. And it doesn't have to be 2D. I did it 2D obviously so we could visualize it, but you'd probably get better performance if you didn't collapse all the way down to 2 dimensions. Okay. All right, so that's operational design domain monitoring. So again, this is just checking like we've defined some domain we expect our system to operate in. How can we just tell if we're outside of that domain? Now we're going to talk about something called uncertainty quantification. And the basic idea here is just that it's helpful to understand our uncertainty in the various aspects of the current and future behavior of the system. Because if we're like uncertain about what's happening right now or what's about to happen, we might want to flag that situation and again, like transfer control back to a human or enter some sort of safe mode. So this is actually like using some model of the behavior of the system and trying to quantify our uncertainty. So that's basically what we do. We'll create a model that predicts some aspect of system behavior. So it could be predicting the current state of the system. It could be predicting the next action of the system, something like that. And then we understand the uncertainty in that prediction to understand what's going on. So for example, maybe we train our robot to say like, I think I'm 2 meters from the wall, but I'm only 60% sure of this. And then we can take that information and decide what we want the robot to do from there. Okay, so there's 2 types of uncertainty. And I'm gonna give a little demo on each of them to help you learn what they are. And so the first type of uncertainty, we're going to do a little exercise here. So this is 2 pictures. I guess you can't really see what's in them at all just yet. But one of these pictures is Mykel, and Mykel as a teenager. And one of these pictures is Matt Damon, who he supposedly looked like as a teenager. And so who he did look like as a teenager. So I'm going to
age as gracefully.
He didn't age as gracefully.
I wonder if Matt Damon's gonna watch this.
we can try to make it happen. Okay, so I'm gonna have you try to guess which one is which. Right now they're kind of too dark, but we're gonna make them progressively a little bit brighter. So let's go 1 level up. Can you tell there's people in there? I can tell on my iPad, but maybe not here. All right, let's go 1 more. Okay, you can start to see the outline of some people. All right, which one do you guys think is Mykel? The one on the right?
Yeah.
The one on the left?
I can see a semicircle.
There seems to be... You're confident?
Very confident.
Left?
Left, for sure.
How about now? Has your confidence increased?
Left, certainly left. Certainly left.
Left.
Okay. Yeah, Mykel's on the left. Although I still can't really tell. I don't know.
Pretty close.
I'm still a little bit uncertain here. But my certainty, and hopefully your certainty as well, has increased as we increase the brightness of those photos. And that is an example of output uncertainty. So when they were super dark, you didn't really know which one was Mykel and which one was Matt Damon. And when they were light, maybe you still couldn't really tell, but maybe you were slightly more certain that this one was in fact Mykel as a teenager. Okay, so that's the idea behind output uncertainty. Here's model uncertainty. So can anyone tell me what this is? Okay, that's kind of the point. So you guys don't have an internal model for what this is. It turns out that this is a picture from the early days of image generation, early days being, I guess, 2022, where this was like DALL-E, and someone asked it to generate a photo of a bottle of ranch dressing testifying in court. So that's what this is supposed to be, I guess. But this is model uncertainty because your internal model of the world probably doesn't have a bottle of ranch dressing testifying in court like inside of it, because you've probably never seen that before. I know I certainly haven't. And so this is model uncertainty. It's like a lack of data or a lack of knowledge about the world. Okay, here's one more example of model uncertainty. Okay, so go ahead and study these for a second here. It shouldn't hopefully take too long. It's not a trick question. Okay, what is that expression? 5. Yeah, okay, there wasn't anything crazy going on. Okay, what about this? Yeah. You have an answer for this one?
Why are we not 12? Wait, what?
Sorry, 3?
What? Wait, where did you get that?
I'm assuming it's
He speaks
multiplication.
Unicode.
Oh, okay.
Yeah.
This is good. So you could accidentally have models be confidently wrong. Oh no, it's good. The point was to like model uncertainty. You just don't know what this is.
Sure. Okay.
So we'd rather our model throw up its hands and say I don't know than just assume. Yeah. Do you have a question?
That's right. So what is the like Mykel, Matt Damon, and output of? Like
Which one is which?
Output uncertainty.
The output is like whether it's Mykel or Matt Damon.
Oh, like but
You're uncertain in that output.
oh, I see. So I am the policy, and I'm so.
You're the policy. You're the policy here too, and the ranch dressing, you're also the policy.
Wait, no, but the policy is
Or the model. Like we're looking at your internal model, and we're saying, is your internal model, what is your internal model's certainty or uncertainty of which one's Matt Damon and which one's Mykel? And here we're saying, now you have this model that you got, and then you used that internal model to calculate this one. Your internal model knows nothing about what like cry face and upside down face does, and so then you would just ideally say like I don't know what this is. It's like model uncertainty. Yeah.
Isn't this just more like out of distribution situation where this is just something we have no concept of at all, but there's not really any uncertainty here because I can't be like, it's maybe it's this or maybe it's that, and I would say 50-50, but instead I'm just like, I have no idea at all.
Well, there is uncertainty, right? The fact that for like upside down faces minus and crying faces divide is like.
Yeah, I think it's debatable, and I've gone back and forth myself a lot about this. I think we've gone back and forth about this. I think like the way I'm going to present model uncertainty later is like very similar to just like a binary, like are we uncertain, are we not uncertain? Because I kind of agree with you that it's pretty tough to define a scale of uncertainty there. But the way we come at it is from like a probabilistic perspective. So that's why I would call it uncertainty. But I agree with you. I think it's like hard to really define.
But it's still like, what's the test to know if this is uncertainty, output uncertainty or model uncertainty? Like from what the examples that I just saw, it would be the first one, it's within the ODB, but I'm there, but I'm just a little bit uncertain, and I can you do ECE, which you probably get to, but it's going to some level of probability on the output I can scale. This one is way outside ODB.
Yeah, I think that's exactly right. So like to kind of summarize what you just said, so it's like output uncertainty occurs when a single input can lead to multiple different outputs. So like maybe we have randomness in the real world due to other agents. So it's like I know exactly where I am, but like I don't know what these people are going to do. But I know that I don't know what these people are going to do. But it's just not something that I can know. Or like the outcome of a coin flip, heads or tails. Like I know it's going to land heads or tails, and I know I'm not sure which one, but like one of those is going to happen. And another common example would be like sensor noise. So we know that our sensors are noisy. We know that one state could lead to different possible observations because our sensors are noisy. We just don't know what those necessarily are. So a lot of times this is referred to as aleatoric uncertainty or irreducible uncertainty. It's just like inherent in the world. And then model uncertainty occurs due to limitations of the model that we're using to predict our system behavior. So for example, due to a lack of data. And so we could call this epistemic uncertainty sometimes, or some people call this reducible uncertainty, because if we just learned about that topic, then we could make our predictions.
What were those emojis?
I don't know. Just multiplication and division. Yes. But you had them backwards.
ChatGPT gave an answer. Wow. With some reasoning. The first one is 5.
That was right.
That was right.
Did we get the second one?
I'm a little confused by this hallucination.
Okay. Sounds good. Okay. So just to illustrate this here, say we have a very simple data set that we're going to use as like a running example. where we have some input point x and some output y, and then here's our data points that we have to learn this model. And so here we have low output uncertainty, they're kind of all clumped together, and then over on this side we have high output uncertainty, and then in the middle here where we have basically no data at all, we have high model uncertainty. Questions on that? Okay. All right, so we're gonna start with output uncertainty. And output uncertainty is present in the data that we gather from the system. So we're in our operational design domain, we just know that there's like this inherent uncertainty in the world. And so because it's present in the data that we gather, we can actually then use this data to train a model that can quantify this uncertainty because we can learn it from the data. And we do that by training a model to output parameters of a distribution over its prediction. So we're not just going to predict the current state we're in, for example, we'll predict the current state we're in with some variance around that state. And so to do this, we get to throw back to my favorite derivation ever that I showed you in lecture 2, where we basically derived the least squares loss function by making an assumption that our data was generated by applying some function to our input and then applying some Gaussian noise to it. And if you remember, we plugged this all in and we maximized the log likelihood of the data, and we saw that that was equivalent to the least squares loss function. But the key assumption that we made when we did this was that the variance is constant. So we said, we add Gaussian noise to it, but with some constant variance. It does not depend on our input. And now we want to actually quantify, given our input, what is our current uncertainty. And so we're going to allow that variance to vary. So we have non-constant or varying variance. And we're going to instead say that our mean or our prediction, which we were calling f before, is a function of x. So this is the same as before. But now we're going to say we're also going to allow our variance to be a function of x. So before, when we were doing this optimization, we could just get rid of the variance because our theta didn't depend on it. But now we're saying that our parameters theta predict both the variance and the mean, so we have to keep those terms in our expression. But we just follow the exact same process, and now we get a kind of loss function that we could optimize that contains both the mean and the variance. So we could learn both of those from our data. So this is basically the loss that we would plug in when we train our model. And just to give you some intuition here, if we look at the terms that are present in this loss function, so we still have this mean squared error term that we had before, but now we have some stuff that has to do with the variance that it outputs. And the second term here is just the log of the variance, and we're trying to minimize, so it says minimize the log of the variance, so make the variance small. But then the second term, we also want this term to be small, as we're trying to minimize, but the variance is on the denominator. And so in this case, making the variance bigger will actually make this term smaller. And so basically what we're saying here is like there's two ways to make this term small. We can minimize the mean squared error between the output and our prediction, or we could increase the variance. And so the idea is in points where we can't minimize this mean squared error because there's all sorts of output uncertainty, and so we can't make a prediction that like perfectly matches all of our data points, then we'll try to make this variance high. So it's basically saying make the variance high in areas where the squared error is high. So in areas where we can't make as good of a prediction, we want to output a high variance. And then in general though, we want to output a lower variance, and it turns out if you balance them in this way, you'll actually get like a calibrated output uncertainty, which I think is super cool. So here's what this would look like. Here's our data set that we were using as a running example. And I actually just trained a model using this exact loss function to output both the mean and the variance. And here I'm plotting the mean of the model as this blue line here. And then I'm plotting 2 standard deviations away as the shaded region there, plus or minus 2 standard deviations. So we're assuming this is Gaussian, so that should contain about 95% of the data. And you can see that it pretty much does. So it actually works quite well, and this is like a very standard practice for quantifying the uncertainty of regression models. Any questions on that?
I guess one thing is that where we have no data, it's still pretty confident. right? So that's maybe not
Okay. Yeah, I'm going to talk about that in a little bit. But basically, like, yeah, you can't really trust the uncertainty in this region. Yeah, that's a good point. Okay. So now we can say where we have low variance, it corresponds to low output uncertainty, like we were saying when we looked at the data before. And where we have high variance, it corresponds to high output uncertainty. Okay, for classification models, a lot of classification models by default already actually output a distribution. So any classification model that applies a softmax function at the end already outputs a discrete distribution because it'll output these values for the classes that sum up to 1. So we take the softmax out of the output, and then, for example, we can now say that we're 80% confident that class number 1 is the true label. And then in general, we could say like this type of a distribution has low uncertainty, and then if we're kind of equally confident that each class is the label, then we have pretty high uncertainty in what the true class is. And so in this scenario, we would be more concerned and more likely to like flag that scenario for runtime monitoring. Okay, but there's an issue here which has been shown a number of times, which is that we often end up actually having an issue with the calibration of the output distribution. So there's this really cool paper from a while ago that talks about how modern neural networks tend to not be well calibrated. So if you just train a neural network with a softmax layer on the end, the softmax probabilities are probably not actually the probability that it's correct. If you remember from chapter 2, when we were doing model validation, and we were plotting like these calibration curves and stuff, and we had this curve that was supposed to line up with y equals x. You can see that this blue model here, which is like a modern neural network, doesn't seem like it's very well calibrated. So in general, this is just like an issue that comes up quite often. And the reason for this is that it turns out that if we were able to perfectly minimize the log likelihood when we were training our model, then, so that means we had like infinite data of the distribution we were trying to match, we had infinite model capacity, and we were able to get like the global minimum of that model, then the output distribution would perfectly match the true distribution that we care about. But of course, in practice, that's like never the case. So training is always approximate. We never have infinite data. We never have infinite model capacity. And so we need to typically apply some additional techniques after the fact if we actually want to have a calibrated model that we can trust the uncertainties for. Okay, and so I'm just going to go through like one really short calibration technique because we don't have much time. But if you're interested, there's more information on this in that section of the book. But one thing we could do is something called temperature scaling, which is really simple for softmax classification models. So here's our softmax function. And essentially all we do is add in this extra parameter called lambda. And it basically adjusts our softmax probabilities. So by the way, also sometimes this lambda is written as 1 over t, and t is called a temperature parameter, and that's why it's called temperature scaling, but these are like equivalent formulations. So we have various values we could pick for lambda. If we pick lambda equals 1, this just reduces to the typical softmax function that we always use. So we'll just get the probabilities we had before. If lambda is equal to 0, then we get exp of 0, which is 1, and this is also going to be exp of 0, so it's going to be 1 divided by the sum up to k of 1, or 1 over k, and it's going to be that same thing for all of our classes. So it's basically just going to tend towards this like uniform probability across all of our classes. And if lambda is equal to infinity, it's going to go in the opposite direction, and we're going to assign all of our confidence to the maximum class. And so ideally, we probably want to be somewhere in between here, but we know that this was not calibrated properly, and so we want to basically pick a value for lambda that gets us a better calibration. So again, we can pick a value for lambda that minimizes the negative log likelihood on a calibration set. So we have some set of data, we'll pick a value for lambda, compute the negative log likelihood on all of that data, and then pick the value for lambda that does the best. So I'll show you what that looks like real quick. Okay, so here's some data I trained for a model that is trained to predict the action for the continuum world problem. And you can see when lambda is 1, so that's when we do no temperature scaling, it doesn't seem like it's calibrated super well. We're kind of not matching this line y equals x. And then what we can do is we can actually vary lambda and plot the negative log likelihood over this calibration data set. And what we want to do is try to minimize the negative log likelihood. So we'll try to move lambda to the right so we get to like the minimum of this negative log likelihood, and then we get something that's a little bit closer to calibrated. Because we're only varying one parameter, we're never going to necessarily be able to get it to be perfectly calibrated, but we can just do our best by picking kind of the minimum negative log likelihood. And then of course, if we like make lambda really high, then we get this very bad calibration, and same with if we make it or too low, and same if we make it too high. Any questions on that? Yeah. What is a calibration data set? It would be data, it's basically like a validation data set, but just like another one on top of that that you're using to calibrate your model. So it should come from like the same distribution as the data that you trained on. Or I guess it doesn't have to. It should come from the distribution that you expect your model to see when you deploy it in the real world. Okay, so we can also, so that was one way to quantify uncertainty, where we like output these distributions and then maybe we calibrate them because sometimes they're not necessarily going to be calibrated. But we can also use these things called prediction sets, which I'm probably just going to go through really fast due to time. But the idea here is like we can, instead of outputting a distribution, we can output a set and just say like we're this confident, which is our coverage. Say we're like 95% confident that our true output is in this set. So for example, maybe our robot is like, I think I'm right here, plus or minus 2 meters, and I'm 95% confident that I'm like here, plus or minus 2 meters, and that's our prediction set. So one way to get a prediction set, and again, I'm going to go through this kind of fast, so happy to talk offline about it, is like maybe we want a prediction set with 95% coverage, and we know this is our distribution over the output. So we could just take the 95% interval, or 95% probability mass of this distribution, and then that would define our prediction set. In a classification task, maybe we want to have 95% of the probability in our prediction set. So we're basically just going to include classes until we've accumulated 95% of the probability mass. So that would be something like this. And then we can use these prediction sets to understand whether we have high uncertainty or low uncertainty. So the bigger the prediction set, the higher our uncertainty, because we're like, I'm 95% confident that I'm here plus or minus 100 meters. Okay, I'm quite uncertain in where I'm actually at, versus I'm 95% confident that I'm here plus or minus 2 centimeters. Then I'm like pretty certain where I'm at. Okay, so an issue with this approach, just to go a little bit more quickly, this would assume then that our output distribution is calibrated, because we would have to take that uncertainty set. If our output distribution is not calibrated, we're going to get the wrong uncertainty set. So one thing we could do is we could just use all the methods I talked about to calibrate this distribution first, or we could take everyone's famous buzzword these days and apply something called conformal prediction, which is everyone's favorite. And conformal prediction basically allows us to generate accurate prediction sets even using an uncalibrated uncertainty measure. So I think that's like why it's so popular, because we can generate these prediction sets without having to do that calibration step that I talked about, which is kind of cool. So that's the main takeaway I want you to have, because I put this in here to like make sure I stayed on track because I want to finish. So it's 2:32, so we're going to be skipping to model uncertainty, and here's a paper. It's super good though, so if you haven't gotten into conformal prediction and like just want to get an idea of what's going on, this paper is really, really good. And they also have a YouTube tutorial that goes with it that I think is also really good if you're like more into watching videos, which I am. Okay, so I'll just flip through these. Here's how it works, but we're not really going to talk about it. Okay, that was output uncertainty. Okay, so now there's this idea of model uncertainty. And so you might ask, which we were kind of talking about before, is like, why can't you quantify model uncertainty in the same way? And the reason is because model uncertainty is typically due to like a lack of data. So we don't have data in this region. And so there's no reason to expect our uncertainty estimate to be calibrated in this region because we have no data there. And so maybe the data we were missing actually looks like this. And we have no reason to believe like that couldn't be the case, and we just don't know. So we can't expect our uncertainty estimate that we predict using output uncertainty methods to actually be calibrated and also allow us to predict model uncertainty. Okay, so then what do we do about this? Okay, so here we go again. Why pick just one model when we could maintain a distribution over all possible models? And so again, we're going to take a Bayesian approach here. And the idea is that basically there are many possible models that we could use to fit this data. So all of these models here actually fit this data pretty well, but they look quite different in this region in the middle here, which indicates to us that we have high model uncertainty in this region in the middle. And so the way we're going to define this is we're going to say that there's a distribution over possible models that could have generated this data, and we're going to call that p theta given d, where theta is the parameters of the model that could have been used to generate the data. And then when we want to make a prediction over a new point, we're going to use this expression here, where we say the probability of the output given the input and the all possible models, basically, is going to be the integral over all possible models of the probability of the output given a specific model. So if we knew our model was given by the parameters theta, what would be the probability that we got that data point, times the probability of that specific model given the data that we have. So this is kind of a Bayesian approach. And specifically, this technique is called Bayesian model averaging. So all we're doing is we're saying there's lots of models that can fit this data. And so we're not just going to pick one. Instead, we're going to average over all possible models to get our output. Okay, but as you might imagine, there's an integral here, and we're integrating over all possible models. That feels like it's pretty intractable, and it turns out in general, performing this computation is intractable. And so one thing that we could try to do instead is use MCMC to draw samples of theta given our data. But you could imagine sometimes theta is the parameters of an entire neural network. And so people have explored ways to try to do MCMC like this. But in general, it's quite difficult to also do this MCMC, and that could even be intractable depending on the model class that we're interested in. Okay, so what do we actually do about this? It turns out one thing that tends to work really well in practice is that we just approximate Bayesian model averaging by creating an ensemble of models, so we'll call that this fancy M here, that all have high likelihood according to p theta given d. So all those models that I was showing on the previous slide, they all fit the data well, so they would all have high likelihood according to this probability distribution. And then we just approximate the integral by basically averaging over all of the models in our ensemble. So what this looks like is maybe one way to do this is we just start, we're training a neural network or something, for example, and we just start with a different initialization, perform our optimization, and hopefully that puts us in basically different local minima of our loss function. And so then we end up with a whole bunch of models that have this high p theta given d, or low negative p theta given d, and then we get this kind of distribution over possible models, and then we could know here by taking the average of our models that we have high output, high model uncertainty. Yeah.
I feel one place where this also comes up, maybe even more naturally, is in the Gaussian process. I know people are planning to talk about it, but I think maybe many people know it, and it's an even more natural application of this, where you just basically have a prior uncertainty that's quite large, and then only if you're kind of certain about it, the uncertainty kind of reduces. Right? And I feel like this would be also very.
So I actually generated this figure using a Gaussian process. Don't tell anyone. But yeah, I think the one challenge there is like Gaussian processes tend to not scale super well to higher dimensions, like super high dimensional things. So that's like.
Yeah, but they have supernaturally encoded the ideas of the model uncertainty and the aleatoric uncertainty kind of. It's like right in the definition of
True.
Yeah.
Good point. Which is why it was very easy to generate this figure using Gaussian process. Yeah.
So I have it's a question for the figure on the bottom left. It seems that as your loss function becomes more convex, then this becomes more difficult because you're more likely for your ensembles to collapse at the same parameters. So then, are you still able to use ensembles in some sense? Like how would you get the parts of your ensemble to be sufficiently split up?
Yeah, that's a great question. I'm going to show an example of that in a couple of slides. But to answer your question about like how to address it, I won't really talk about that, but there's like various, I think there's something called like randomized prior functions or something. Basically, you like, if you're training like an ensemble of networks, you kind of first train them to represent different functions, or like in the loss you have them represent different functions, but then in the spot where your data is, it should collapse to the thing that you want. So there's like various ways to try to encourage this like extra diversity in the models in your ensemble. You can also like try different model architectures so that they're like less likely to have like some common local minimum. But in general, it's like something you have to worry about. So, yeah, no question. Yeah.
And sometimes if your data is entirely convex or quite convex or true data, then this is not a problem, right? Because if it's truly convex, your model will fit super duper well.
Yeah, I guess if there's one global minima,
none of this is actually
then
a problem.
you're okay.
Yeah.
Yeah. I would say typically that's not the case, but yeah. Any other questions? Okay. So just to give another example, we could do this also for classification models. So let's say that we wanted to train a model to predict the action that's taken in all of the states that we have for our continuum world. We could train an ensemble to do that. And then, for example, in areas where we have no data, it should average out to a model that basically just has equal probability for all of the different actions. And then where we do have lots of data, then we get very certain which action we think we're going to take. Okay. So yeah, to get back to the question we just had, a problem to watch out for with ensembles, so we hope that this happens, they end up in a whole bunch of different local minima, but there's not necessarily any reason to say that this couldn't happen where they all end up in the same local minima, and then they all just collapse to the same thing, and then it was a few minutes ago, they're going to be very confidently wrong about, sorry, Robert, just boosting your confidence before your defense. So yeah, this could happen, and it's actually happened to me when I've applied ensembles in my research. Like they're all wrong in the same way on some data points, and then yeah, it's something that you kind of risk there. So in general, you should try to ensure sufficient diversity. I think in the book we do cite like one paper about how to do this, but in general, like yeah, this is an area of research that people have looked into. Okay, so I think we're about going to make it here. So the next thing, so we've determined, so here's how I would kind of see this being deployed on a system. One thing we do is we determine if we're in the operational design domain. So that's kind of the first check that we have. Like, are we even operating in like the region that we validated over? Then maybe we try to quantify our uncertainty within that region. Model uncertainty I would actually still kind of categorize with point number one a little bit as well. But then let's say, okay, we're like good with our uncertainty. We know we're in our operational design domain, but we just did a whole bunch of offline validation and we found that failures do still sometimes happen within our operational design domain. So even though we know that we're in this region that we validated over, that we trained on, we still might fail. And we might want to monitor for that kind of along the way. And so that's basically the idea behind failure monitoring, is that we've determined that we are operating within the operational design domain, but we still could potentially be in a dangerous scenario. But the difference here is that we know about it because we've done this validation and we know where these failures might occur. So there's various things that we could do here. Basically, the simplest thing you could do is you could just like run a bunch of offline validation algorithms online. So you could just like run reachability analysis online from the exact state that you're at. You could do a bunch of rollouts out online from the state that you're at and try to get an estimate of the probability of failure. Obviously, these are things that could potentially be computationally expensive, so it might be difficult to do at runtime, but these are things that you could do. Another thing you could do is like say you calculated the probability of failure from all of your states offline, maybe using like the probabilistic reachability analysis we talked about. And so now we have this idea of the probability of failure. Given our current state, if we were in any of these red states, we would have a high probability of failure. And then we can just store that online and monitor whether we're entering into any regions or states where we have a high probability of failure. And so then maybe we would just kind of monitor this as we go. It's a good animation to end on, right? I'll play it one more time. Here we go. It's actually flying into another plane, but yeah. All right, one more time. Why not? Okay. Okay, cool. Any questions on failure monitoring? There's more in the book about this. I'm just talking about it briefly. Okay.
I would say that one thing that, from a computer vision standpoint, all the computer vision systems I have deployed, we would very frequently do TTA, is what it's called. It's specifically in the computer vision literature, test time logs. And so and it's covered a little bit, but I'm not looking at the probability. It's usually for detection and it's post. So provided it's above 0.5 probability, the bounding box is above 0.5, then I would keep it. And if I do logs to the image and the thing goes away, or it's still there, if the box goes away or it's still there or it changes, then that's uncertainty. So it's the variance in the output, not the absolute value, like the absolute value, right? And
you would like augment the image in a few different ways, or like perturb it, and then.
And this is done all the time in self-driving. So you'll run on 100 versions of every image, because your ComNet is like we implemented in like firmware. It's like as fast as possible, especially FPN, like that's the base for all models. And then you push it out and you'll run 100 version logs of every single image, especially when you have exposure issues and all that stuff. So that would be my only comment to what did you call it? You called it
Bayesian model averaging?
Yeah.
Yeah.
No, it's not model averaging, because the model stays constant.
Yeah, it's more like data averaging what you're describing.
Yeah, you had a name for it, but yeah.
Oh.
I think that's like sensitivity.
Okay.
Yeah, maybe it's sensitivity.
It's sensitivity.
Yeah. But cool, that's interesting to know about. Okay, course wrap up. Here we go, guys. All right, so we started with this. We talked about how in other courses you mess around a little bit. In this course, you're going to find out. So I hope you feel that you have sufficiently found out now. Or maybe with the project 3 and the final project, you'll feel that way. We talked about lots of different methods for validating systems, all the way from failure analysis, formal guarantees, explanations, and then today we just talked about what to do when you deploy the system at runtime. But hopefully you noticed that there was kind of holes in all of these various methods. There were limitations that we talked through as we were going through all of these methods. But again, with the Swiss cheese model, the idea is that these holes or limitations hopefully don't line up. And so if we can apply enough of them at once, we can build a safety case. So I just want to remind you that there's no silver bullet here in safety validation. We need to build a safety case. And hopefully this course gave you a good starting point for how to do this. And there's lots of open questions that maybe have even come up during lecture that are still need to be solved for all of these various techniques. So if you're interested, I think it's a really good area of research to go into. And so there's lots of research you can do, and hopefully also these will be helpful tools as you go into industry. Okay, so thank you all so much for being part of this first edition of this course. I've had so much fun doing these lectures with you and seeing all of your questions that you have and all the projects that you've done. It's been a super great time for me, so I really appreciate you tagging along for the first edition. Definitely stay in touch and reach out if you ever need anything, validation or otherwise. You have my email, super happy to keep in touch. And I just want to wrap up by saying that sometimes you might find out in not the best way possible, and you might find yourself, knocked down a little bit. But if you do find yourself in that situation, I hope that you will laugh it off and get back up and take another swing at it. So, yay.